Okay, today we're going to go through the first section in the book, Chapter 1, Relations and Functions, Section 1.1, Sets of Real Numbers and the Cartesian Coordinate Plane. So starting at the beginning, we're talking about what a set is. And set is just a fancy word that means a well-defined collection of objects. And we'll call the objects in the set elements. Now, we can have mathematical sets that contain things like numbers or graphs or lines in them, but you could also have the set, say, of all people in this class, or the set of all foods available on a given menu. Set just means a list of stuff, basically, and you have to have a good rule for that list of stuff. We can have mathematical rules if it's numbers, or the rule can just be all the things that are written on a specific menu. Nothing fancy going on here. Set just means a list of stuff. Now, there's a couple ways that we can define a set. So, for example, verbally, we can just describe the set using words. The set of all even numbers, for example, or the set of all things on this menu. With the roster method, we use curly braces to determine each unique element in the set, and we literally just list them out. So, for example, we might say, okay, the items on this menu include fried rice and egg rolls and General Tso's chicken, and you just list them all out, and you use the curly braces around it to list them all out, and you separate each one with commas. The third option, potentially the most powerful one, is the set builder option. Sometimes a set is too long to write out, and sometimes, in fact, you can't write it out because it's infinitely long. So maybe you can use ... dots to kind of show a pattern, but sometimes it might be better to use set builder notation. So what this is going to do is we're going to use a dummy variable, and we're going to describe a rule that works for the set. This is very helpful in math for describing sets that are made up of more common sets. So for example, we might say that the set of even numbers is all of the integers that are divisible by 2. So let's show an example here, and let's do this with the sets of even numbers. We want to be able to write out the set of all even numbers using each one. So the first one here is verbal. And all we need to do here is we need to say the set of even numbers. Nothing fancy in the verbal method. Now, if you don't know what even numbers means, that might not be specific enough. So the next thing we can do is we can talk about the set builder method, or the roster method, excuse me. In the roster method, we will go ahead and we will list out the even numbers. Now, there's infinitely many, so this won't actually be everything. What we're going to have to do is we're going to have to do a ... So let's say I'm going to start at -2, 0, 2, 4, 6, ... And this does a good job of showing off the pattern a little bit. But the issue here is that, first of all, we might not be able to guarantee that the pattern continues forever. We can guess that it does, but we don't know. And of course, we haven't been able to write everything out. So in this case, the set builder method is particularly powerful. And when using the set builder method here, what I'm going to do is I'm going to say I first need to describe the type of thing that I'm going to have. So this just means, looking at this notation, x is my dummy variable. So I'm going to describe the rule that applies to x. This symbol right here means in the set. So x is in the set, and then we're looking at specifically the set z. Now z, you may not know this, but z is the set of integers. Put all together, these three symbols here means x is in the set of integers, or x is an integer. Then I've got this colon, which you might read aloud as such that, and now we'll put the rule. So first we're describing where x could possibly come from. X isn't something from my Chinese food menu. X isn't a student in this class. X is an integer. What kind of integer is x? X is an even integer. So we might say x is, let's say, divisible by 2. We can write out this rule in words. We could use more symbols to write the words out. If you know a symbol for the word divisible, you could use that. There's lots of different options that we can take here. But the whole point is the same. We begin the first half with where x is from. And then the second half is a rule for x. And it doesn't have to be x. X is, of course, one of the most basic variables, so we'll use that frequently, but it could be any variable at all. Sometimes we might even need more than one variable, and we'll see that in the next section. Now, there's a couple of sets that we're going to want to be familiar with. Building up from smallest to largest, the first set is the set that has literally nothing in it. If we can think of a set as a bag containing objects, then the empty set is a bag with nothing in it. It has no objects, no elements, and that can be very helpful when you want to talk about specifically having nothing. Then we want to look at a bunch of different types of sets of numbers. So the first one we're going to have is natural numbers. These are our regular old counting numbers. 1, 2, 3, 4, 5, and counting upwards indefinitely. 10, 20, 1,000, 378. Any regular counting number starting at 1 and going upwards is called a natural number. The whole numbers are exactly the same, but they add an extra piece, 0. We've also got the integers, which includes all of those same whole and natural numbers, but also includes the negative numbers. It goes back and forth in both directions, so any positive or any negative regular counting number would be an integer. To make an even larger set, we want to allow ourselves to do fractions. That's what we're going to call rational numbers. A rational number, you can see here a really nice example of set builder notation. A rational number is any number that can be written like a fraction. We've got the fraction written in the form a over b. A and b have to be integers, and because we can't divide by 0, we'll make sure we say that b cannot be 0. This is a really good example of set builder notation because it shows off our rule describing a pattern. Remember that rational numbers could be all fractions, or we can also think you may have heard as either terminating or repeating decimals. So whether you can write it as a fraction, like 1/3 or 1/2, or potentially like a decimal that either stops, like 0.5, or one that goes on forever, like 0.3 repeating. These are all good examples. You might put the repeating sign as a bar over it. This means the same as these things. So all three of these are the same way to write 1/3. Bigger than rational numbers even is real numbers. There are some numbers that we can't even write as a fraction. A couple of examples of these numbers that would be not rational, which you can see is the next step we're looking at, irrational numbers. Pi is an example. You can't possibly write pi as a fraction. The square root of 2 is a good example. Most square roots, in fact, will work. Any square root that doesn't come out to be an integer is going to end up being irrational. The real numbers makes up the rationals and the irrationals together. This symbol right here, this backslash, means that I'm taking all of the reals that are not rational. If we can think of this as a diagram where I've got all of the reals, and within the reals, let's write this way instead, make it a little more clear. So I've got this set containing all real numbers. And then I've got the integers, sorry, not the integers, the rationals, and I've got the irrationals. Sometimes we'll call the irrationals P, or sometimes I. I'm going to use P here to match what the textbook uses. We've got these different types of things, and since the rationals and the irrationals together make up the reals, if I take the reals and I drop the rationals, what I'm left with is irrationals. We can further go with this diagram here. So within the rationals, we can get the integers. And then within the integers, we get the whole numbers. And the only thing different from whole numbers and natural numbers is 0. And now we can kind of see how these things play into each other. Natural numbers is the smallest set that contains numbers that we're looking at. Slightly larger than rationals is the whole numbers. Then we've got the integers. Then we've got the rationals. And if you put the rationals together with the irrationals, which don't actually overlap at all, you get the real numbers. There's one even bigger set than that, and we're barely going to look at it at all in this class. Maybe a little bit towards the end, maybe a little bit more in pre-calculus too. We've got the complex numbers. The complex numbers are going to include imaginary numbers. You may have seen square root of -1. If you've only worked with real numbers before, you'll probably are thinking that negative numbers don't have square roots, and within the reals you'd be correct. Complex numbers is a way for us to allow negative numbers to have square roots, and it can sometimes be very helpful. For the most part in this class, however, we are going to concern ourselves with real numbers. I would say the most important ones to know are reals, rationals, integers, natural. I would say those are the 4 most important, and then second most important, I'd say, is empty set and irrational. We'll come back to complex much later. Whole is just kind of nice to know, but we're not going to use it nearly as much as the others. Now, other than these standard sets, we often want to describe several different types of sets. We already talked about even numbers being one example. Very often we want to talk about all of the numbers between 2 numbers. For example, if I want to say everything between 1 and 10, I might want to say that. But then I have a question here. When I say between 1 and 10, do I just mean 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Or do I want to include fractions? Do I want to include rationals or irrationals? What's going on there? Is 1 included? Is 10 included? What am I actually counting when I say between 1 and 10? So to make it more clear, we've got this idea of an interval. Interval notation allows us to write all of the numbers between 2 numbers. And we're always going to, when talking about an interval, say that we want all real numbers between those 2 numbers. So for example, if I want all the numbers between 1 and 10, then I'm going to be including 1, 2, 3, 4, 5, 6, 7, 8, 9, all of those from 2 to 9, and also all the fractions and decimals and even irrationals as well. So like 1.7, for example, will be included. The question of whether or not to include 1 and 10 is a good one because sometimes we do and sometimes we don't. So we're going to have several different types of intervals. This first one here, I'm just not including the endpoint. So everything between 1 and 10, but not including 1 and not including 10. That's going to be called an open interval, and we're going to mark that with these open parentheses. Here is the set builder notation for this. If I was going to graph this interval, what I might do is I might say here is 1 and here is 10. I don't want to include 1 or 10, but I want to include everything just past it. That's not going to be 2 to 9 because there's fractions between 1 and 2 and fractions between 9 and 10 that I do want to include. So to symbolize that I don't want to include 1, but I want to include everything afterwards, I'm going to put an open circle. Similarly, at 10, I'll put an open circle, and then I'll connect this with a line. And what this means is I want to include every number that's larger than 1 and smaller than 10, but not 1 and not 10. I could also do the same thing if I want to include them. The difference in terms of the graph is that I will put a closed circle instead of an open one. Filling in that circle represents the fact that I want 1 and 10 to be included, not excluded. To represent this in terms of the interval notation, I will put square brackets or closed brackets around my numbers. This symbolizes that I want to include 1 and 10. So everything from 1 to 10, including 1, including 10, and including all numbers in between, including fractions, decimals, irrationals, rationals, all of those together. Sometimes we want to include one but not the other, and in that case we would mix and match the symbols. We would use a closed circle and an open circle, or an open parenthesis and a closed bracket together. You might call this a half open interval. Let's look at a couple of examples here. We want to be able to write each of these sets as an interval, and we want to be able to graph each one as well. So let's start with this first one here. Here's a half open interval because this one is less than or equal to, but this one is just less than. So what I want here, we'll start with the graph, is from -2 to 3. I do want to include -2 because I can be less than or equal. But for 3, I want to not include it because there's this just less than sign. And then I would connect it with this line. In terms of interval notation, I want -2 comma 3, a closed bracket here, and open parenthesis here. It's okay that they're mixing and matching. Same deal with the next problem. Now, one very important thing we need to look at here is that my numbers are backwards. 1 is larger than 0. So I'll need to make sure when I'm thinking about my notation and my number line, I put everything in the proper order. 0 and 1. I don't want to include either, so I'll put open circles in both cases. And in terms of interval notation, 0, comma 1. You can't put 1, comma 0 because that's not in the correct order. It needs to be from the lower endpoint to the higher endpoint. Now looking at this next one, it's a little bit extra because I only have one number that I'm comparing to, 7. I want to include all numbers that are larger than 7 or also equal to 7. So I'll fill in the dot here and I'll draw the arrow. This arrow means keep going forever. So I can take anything larger than 7 without stopping. So my lower endpoint is definitely going to be 7, and I'm using a square bracket because I want to include 7. What I'm going to put over here is an infinity because this symbolizes that I want to keep going forever. Now, infinity is not actually a number. It just means going on and on forever in the positive direction. So because infinity is not a number, it can't actually be included in our interval. That means since it's not included, I'll need to use a parenthesis here. This next problem is very similar and for the exact same reason. I'm going to be looking at all of the numbers less than or equal to -1/2. The fact that I've used y here doesn't make a difference in the world. Everything that I'm doing is still exactly the same. And so what I'm looking at here is a filled in circle at -1/2. Since it says less than, I'm looking to go this way. And for my interval, -infinity is my starting point, which can't be included, so it's a parenthesis. 1/2 is my ending point, and here I did want to include it. The set of all real numbers would literally be everything possible on the number line. We're including everything, which means I want to go from -infinity all the way to +infinity. Again, neither of these are numbers, and so they won't possibly be included in the set. Therefore, I am going to use parentheses on both ends. Now, sometimes you might want to be able to combine sets together. Maybe you've got two intervals that overlap, and you want to consider just the overlap, or else you want to consider both of them. In that case, we can use intersection and union. And to figure these out, it can be helpful to think about a Venn diagram. In terms of the intersection in the Venn diagram, I'm looking at just the overlapping part. So this right here would be A intersect B. Intersect is represented by this upside down cup, or maybe you might call it a cap. And it's all the stuff that's in both the set A and the set B. The union of two sets, and let's put an underline here to color code better. The union of two sets is exactly the opposite. If I've got A and B, I want to consider the stuff that's in at least one of the two sets, or also both is okay. All of this stuff here would be the union of A and B. So we've got one time where I want just the stuff that's the overlap, or the another option is one that allows us to get both. Let's do a couple of examples here with some intervals. Let's say that I want to first, before we would go to intervals, just a basic set of some numbers. I want the union of these two sets and then the intersection. So when I'm looking at the intersection first, and let's underline this to color code again. If I want the intersection first, what I'm going to do is I want to find everything that's in both sets. The only number that I see in both sets is 2. We'll need to write it still as a set, so I want the set containing the number 2. Similarly, for the union, I need to list everything that is in both sets. So I see 1, 2, 3, 4, and 5. 2 is in both sets, but I don't need to list it twice because the set doesn't care how many of each thing you have, just that it is there or that it isn't there. So this will be my union. Now we can do the exact same thing with these two intervals, and it might be helpful to draw them together on the same graph. So let's first sketch these two intervals out. So I have 1, 2, 3, and 5, so we can kind of scale this number line up appropriately. Starting here, my set A goes from 2 to 5. I want to include 2 and not 5. My set B goes from 1 to 3, and I'm similarly including 1 and not including 3. This being due in both cases to the parentheses and brackets that are showing up here. For the intersection, what I'm looking to find is I'm looking to find the overlap of the two sets. So 2 is in both sets, and all the stuff between 2 and 3 is also in both sets. 3 is not in both sets, though. 3 is not in B. So my intersection is this little bit, which would be from 2 to 3, including 2, excluding 3. The union works similar. I want to consider the stuff that is in both. So the union of A and B would be, I see 1 is going to be in B. Everything from 1 to 5 is in at least one of the sets, because all the stuff going up to at least 3 is in A, and then A is in B, excuse me, and then B includes from 3 all the way up to 5. So there is going to be my union from 1 to 5. Let's take some example writing sets as unions of intervals, because this can often be very helpful. In this case, I want to take all of the numbers that are either less than or equal to 2 or greater than 5. It can be very helpful in these instances to sketch the intervals, so let's start with that in each problem. I want less than or equal to 2 and greater than 5. Here, I see that I've got two distinct pieces. This piece goes from negative infinity up to 2, including 2. And this piece starts at 5, though it doesn't include 5, and goes up to infinity. Because I want to consider both of these pieces, I'll take their union. And that gives me my answer. Looking at this next one, what I've got is I've got all the numbers t, but I don't want to consider t equaling 4. That's not allowed. So let's take a look at what that would look like on a graph. Let's add a different color here. 4 is not included, but anything larger than 4 is included, and anything smaller than 4 is included. Now, there's a couple of ways to write this. Because I've asked for a union of intervals, what I want to consider is the two distinct pieces. I've got this first piece going from negative infinity to 4, and the second piece going from 4 to infinity. Unioning these two together gives me the answer I'm looking for. But sometimes I don't really want to think about this as two intervals. I want to think of this as one interval with a piece removed. So I may alternatively use the notation here the entire set of real numbers in this case, except, remember that backslash we talked about earlier, not 4. This is saying I want all real numbers, but not 4. Let's take a look at the last problem here. 2 different pieces. I want the numbers q, where q is either between -2 and 5, where I'm not including either, or it could also be 8. So in order to write these ones, this interval, nothing weird going on here, for this second interval, now how do I write 8 as an interval? If I was going to write 8 as an interval, I would say I want to start at 8 and also stop at 8. This is probably not the best way to describe what's going on here. You usually think of an interval as like a section of the number line, or like a line that has a start and a stop. If it's just a point, usually writing that as an interval isn't the best way, but we can do it. It still works. And unioning these two together gives me the correct answer. It's probably not the clearest answer though. So what I would usually write for myself is I would write -2 to 5 union with, now we want to union with just the point 8, but whenever you use union, union is a tool that combines 2 sets together. So what we should do here is we should put 8 as a set. We're just going to use the roster definition since there's only a single point, no reason to do anything particularly fancy. This is another way to write the same thing, making it more clear that it's the union of an interval and a point. We can see that there's a couple ways to write many different things, and they give us a lot of different information. You'll want to pick out the one that's the most helpful for any given situation. Now, we've talked a lot about 1D. We want to be thinking about 2D. 2D is very helpful for a lot of reasons. First of all, it lets us actually show a relationship between 2 variables. We're going to see a lot of that later on in this chapter. Second of all, it actually lets me draw pictures, not just line segments, but actual graphs. We can graph functions with this, and we'll see lots of cool things. What we've got here is 2 different lines that represent 2 different variables. We've got a horizontal axis, usually that's x, and a vertical axis, usually that's y. I can have a point on here, and what I will do is I will represent with coordinates. This is 3, so the first coordinate is 3, and this is 2, so the second coordinate is 2. It's always going to be horizontal comma vertical, which is usually x comma y. Now, one thing that is very important to be careful about is that a point can often look like it's going to be an open interval. You need to make sure that you are clear that when you mean a point or when you mean an open interval, if it's ever ambiguous. Usually it will be clear which one you're talking about, but it's always good to be careful. Now, sometimes we want to reflect a point in the plane. Reflecting a point, you can think about as having a line representing a mirror and looking at where the reflection would land. There's 3 common reflections we use: through the x-axis, through the y-axis, and through the origin. To flip over one of the 2 axes, all you need to do is you need to flip the sign of the other variable. So for example, to flip over the x-axis, which is the horizontal axis, you might be going from the top to the bottom and making the y-coordinate negative. The y-axis would be the exact opposite. To go through the origin, you can imagine doing both of these things back to back, or else reflecting right through the center of the map. This means that we're going to switch x and y both with a negative number. Taking a look up here at what that would look like, what I end up having is this would be a vertical reflection, which would be 3, -2. A horizontal reflection might look like -3, 2. In each of these cases, imagine reflecting across this line here. For a reflection about the origin, what I'm looking at is something like this. -3, -2. And I can think about this being the line I'm reflecting across, one that goes straight through the origin here. If you didn't know, let me do a different color for this. The origin is the point in the center of the graph, 0, 0. Now, there's a couple of things that we want to do when we're comparing points in the plane. The first is going to be called finding its distance. And in order to understand how you can find the distance of points, you want to look at Pythagorean theorem. Let's say that I had a point here, x1, y1, and x2, y2. And I wanted to find the distance between them. By using the Pythagorean theorem, I can just simply count over and up and then use the Pythagorean theorem to find this distance c. If I was going to solve for c here, what I would do is I would take a square root on both sides. And so c is equal to the square root of a squared plus b squared. But then I can also look at what a is. A is the distance from x2 to x1. And the way I've drawn it here, x2 is larger than x1, but by putting these absolute value bars, it allows me to not care about the order and make my life a little bit simpler. I can similarly do the same thing here. B is the difference from y2 to y1. Putting all of this together and renaming ourselves d for distance, I obtain the distance formula, which is the square root of each of those different pieces. Notice that I don't need absolute value symbols anymore. The reason for this is that when you square a number, remember it will turn positive. So absolute value turning something positive is redundant when I'm also squaring it. Just as a quick example, let's find the distance between these 2 points. It doesn't matter which one I call point 1 and point 2. Let's say this is x1 and y1, and that this is x2 and y2. What I'm going to do here is just plug directly into the formula. Square root of x2 minus x1 squared plus y2 minus y1. So 7 minus 1 squared. Since I'm subtracting a negative from a negative, I'm moving further in the negative direction. So -2 squared plus 6 squared. 4 plus 36 is equal to the square root of 40. I could plug what that is into my calculator, and maybe you would do that if you were about to do some construction with this, but I'm perfectly fine to see the answer in square root form. It's actually a little bit nicer because it's exact form. You won't have to do any rounding here. Now let's suppose that I have a little bit of a more complicated problem. It gives me one of the points, 2, 3, and another point P, which it tells me is on the line x equals 6. It tells me the distance between those two is 5. I would like to find where P could possibly be. Let's take a look at what this would look like. Drawing a graph for myself, it starts with the point 2, 3, which I know is over 2 and up 3. So this is my first point. Then it tells me I've got the line x equals 6. Thinking about this, and we're kind of cheating going into one of the later sections here, but x equals 6 is the line where all of the x coordinates are 6. An x coordinate of 6 would be over here, and I'm considering all points with an x coordinate 6. So this one, this one, this one, this one, this one, and we can start to see how I'm tracing myself out a line. The distance between these 2 points is 5. So I need to think of what the distance would be. Well, if I were just to go straight over, this distance here is only 4. So to get a distance of 5, I'll have to go at a little bit of an angle. And I can either angle myself up to get a distance of 5 or down. to get a distance of 5, which might have the two coordinates 6, comma, let's say B, and this one 6, comma C. We'll have to find these two using the distance formula. So we should expect that we should get out two answers. Both of them have an x-coordinate of 6. One of them is going to have a higher y-coordinate than the other, and I should get out two total answers. So let's make sure that that happens when we solve this problem using the distance formula. So starting off just by repeating the distance formula, and then we'll fill in all of the blanks. 5 is the distance that I'm looking for. Y2 is the unknown number. Let's just put B for now. Minus the known y-coordinate is 3. Similarly, in terms of x's, I'm going from 6 minus 2. I can solve for a lot of this. So let's first square both sides and get 25 is equal to b minus 3 squared. And similarly, 6 minus 2 is 4 squared. So that means I can have 25 is equal to b minus 3 squared minus 16. Plus 16, excuse me. Subtracting 16 from both sides, 9 is equal to b minus 3 squared. And I can now square root both sides. Make sure you're very careful in this step, because when I take a square root, what I need to remember is a plus or minus sign. So plus or minus 3 is equal to b minus 3. Let's treat this as two different problems where 3 equals b minus 3, which means b is 6. Or also, I could consider negative 3 is equal to b minus 3, which gives me b is equal to 0. So that gives me my two different y coordinates. They both came up as b because I didn't set it as two different, but I've basically found myself b and c. So my 2 points are 6, 6, and 6, 0. There we go. One more thing we want to talk about in this lesson, that's midpoint. The midpoint of a line segment, from 2 points x1, y1, and x2, y2 is given by this formula. All I do is I find the average of the x-coordinates and the average of the y-coordinates. It's very easy to find the midpoint. If you're given points, you just plug into the formula. So thinking about the exact same line I had before and just sketching it out to get a sense of what's going on here. There's 1, 1, and then I've got negative 1, 7. What I'm looking for is this point right here halfway. So plugging into my formula, I'm going to have the difference of the two, or the sum of the two x-coordinates, excuse me. So 1 plus negative 1 over 2, and then also 1 plus 7 over 2. This gives me 0 over 2, comma 8 over 2, or more simply, 0, 4. That actually matches up with my sketch pretty well, so it would make sense that this is where this midpoint would be. It's not perfectly to scale, but it's pretty much in the right place. One more problem with midpoints. Let's say that I actually know the midpoint of a certain segment and also one of the 2 points, and I'd like to find the other one. Let's again get a sketch of what's going on here to make our task a little bit simpler. 0, comma 3 is up here. That's the midpoint. I know that I've got the point 2, 2 as my first point. So what I'm looking for is this other point. Let's use the formula to solve this problem here. So I know that 0, comma 3 is the midpoint, which is equal to x1 plus 2 over 2 and y1 plus 2 over 2. In this case, I'm just simply looking to find the x and y coordinates for the point A. I can solve each of these as a separate problem. So 0 is equal to x1 plus 2 over 2, which gives me, after some quick math, negative 2. Similarly, if 3 is equal to y1 plus 2 over 2, y1 comes out to be 4. So A is the point, negative 2 comma 4. Again, this matches up pretty nicely with my sketch of a drawing. It often can be very helpful when you're solving a word problem like this to draw a picture. It won't give you the exact answer, most likely, but you can use that picture to help make sure that your answer makes sense and give you some kind of intuition for what you're trying to do. That's all for section 1.1. Thank you so much and have a fantastic day.